This lesson is on pendulums and was created by Lydia McConan and Haley Brim. Pendulum history. A pendulum is an object or mass hung from a fixed point so that it can swing freely back and forth. Viviana, Galileo's pupil, wrote that Galileo observed the motions of a chandelier hanging in a cathedral and noticed that it has a constant period even when moving at different angles. Viviana claims that was how he discovered the laws of pendulum motion.
Now we're going to talk about pendulum facts. The regular motion of the pendulum can be used for timekeeping, and pendulums are used to regulate pendulum clocks. Equilibrium is the point where if the pendulum mass was at rest, the forces would be equal. Velocity and kinetic energy are at its maximum. Amplitude is the maximum displacement from equilibrium. Potential energy is at its maximum. Foucault's pendulum, named after the French physicist Leon Foucault, is a simple pendulum conceived as an experiment to demonstrate the rotation of the Earth. The pendulum is located in France. Now we are going to discuss variables, units, and definitions. Period, which is represented by the variable of t, is the time needed for one complete cycle of vibration to pass a given point. This is measured in seconds. Pi, which is represented by the variable of the pi symbol, is a numerical constant that represents the ratio of a circle's circumference to its diameter on a flat plane surface. Gravitational force, which is g, is the universal force of attraction acting between all matter. This is measured in meters per second squared. Length, which is represented by L, is the straight line distance between 2 points along an object, which is measured in meters, which is m. Frequency is the number of oscillations per unit of time. This is measured in hertz.
For all the applicable formulas, we have period equals 1 over frequency, period equals 2 pi times the square root of L over G, and then frequency equals 1 over the period.
The question that we are solving today has two parts, and it states, a tire swing has a period of 2.5 seconds. Part A asks, how long is the swing here on Earth? And Part B asks, if the tire swing was taken to Mars, where gravity is 1.6 meters per second squared, what would the new period be?
This diagram shows the swing of the tire on Earth with a gravitational force of 9.8 meters per second squared and a period of 2.5 seconds.
So first we are going to write our givens, which is the information provided to you in the problem. Our first given is 2.5 seconds and is written as t, which is the period. In the problem, it states that the swing is on Earth, which means that g, gravitational force, is going to be 9.8 meters per second squared. The question is asking us to solve for length, which is written as L and has its units in meters. Since we have our givens, we know that in order to solve the problem, we need to use the equation t equals 2 times pi, the square root of L over G. Now we are going to plug in 2.5 for t, 9.8 for g, and solve for L. We are going to divide both sides by 2 pi, and you should get 0.3978. After that, we are going to square both sides to cancel out the square root. Now our problem should say 1.583 equals L divided by 9.8. Then multiply both sides by 9.8, and our final answer will be L equals 1.55 meters.
In our givens, it tells us that the gravitational force is equal to 1.6 meters per second squared, and that our length is 1.55 meters. We got that length from our answer in part A. Now we're going to be solving for t, which is our period, and it's given in seconds. With our givens, it tells us that the correct formula would be t equals 2 pi times the square root of L over G. When you plug it in, it should say t equals 2 pi times the square root of 1.55 divided by 1.6. After plugging in your numbers, divide 1.55 by 1.6 and you should get 0.9687. Then take the square root of 0.9687 and you should get 0.984. Then multiply 2 pi by 0.984 and your final answer should say t equals 6.19 seconds.